This is Phil Coatman with a tutorial on improving your code style to make better and safer use of your programming language. Two important aspects of coding style are human understandability and safe programming language use. In this tutorial, we'll cover the programming language use side of things. There are three warning signs that your coding style does not use the language as well as it should. First, your code should not compile with warnings. Warnings are there for a reason and indicate there is a problem with the language use portions of your coding style. Second, if you manage to compile without warnings because you've turned off the warnings, that's still a problem. Third, if you are only using a subset of all the possible reasonable warnings, that means, in effect, you're back to turning off some warnings, and that's still a problem. The importance of the language use portion of coding style is to make sure the compiler actually understands what you meant to accomplish in your software. A warning might mean that the way you're using the programming language is undefined or compiler dependent. In other words, the compiler might do something, but it might be that all bets are off as to what really happened. For example, even a very minor change in the revision of the compiler or a minor change in the platform you're on might result in the compiler doing something completely different, even for the same source code. This makes code like that bug-prone. On the other hand, a warning might mean that you're doing something that is very well defined by the language, but is a really bad idea. In other words, you might be doing something that the C language syntax happens to define, but is almost always a bug. We'll have some examples of these shortly. While the C programming language gives you a lot of power and control, the unfortunate fact is that it can be an unsafe language if used improperly. In other words, the C programming language does not always play nice. Adopting a good coding style can take the edge off the language and dramatically reduce the chance of bugs. While there are many ways to get bitten by the C programming language, here are a couple examples of defined but potentially dangerous language use. First, most C programmers have made the mistake of putting a single equal instead of a double equal inside a conditional clause. In this case, A single equals B. This has the effect of taking the value of B and putting it into the variable A, and then evaluating whether the result of that assignment is 0 or non-zero as if A were a Boolean flag. Almost always, the programmer meant to use a double equal comparison. Not only does this implement the wrong comparison, but also corrupts the value of the variable A. Another classic dangerous language use in C is inadvertently putting a semicolon after the condition in a while statement. What this code probably meant to do was to decrement the variable x in a while loop, but because of an extra semicolon, what it actually does is infinite loop on the while because x is never changed. This is perfectly valid C syntax, but almost always a bug. A good compiler will issue a warning saying, yeah, I know this is valid C, but that's probably not what you wanted to do. Unspecified or undefined language use can also be dangerous. Sometimes these problems are more subtle because you may think you know what's supposed to happen, but what actually happens varies from system to system and potentially varies even depending on the code surrounding that line of code. The first example is a null pointer dereference. You might be used to this creating a seg fault or program abort. But if your microcontroller does not have memory protection, which is common in embedded systems, a null pointer will result in loading or changing the value of the address 0 memory location. Uninitialized variables can also be dangerous. While in many desktop systems, memory is initialized to 0 on first use, in embedded systems, memory may not be initialized, leading to random values for uninitialized variables, especially after a system reset due to, for example, a watchdog timer trip. Accessing past the end of an array is a security vulnerability and also common enough. One example is if you access the 10th element of a 10-element array, that's an error because in C, the arrays are numbered from 0 through 9. Finally, a somewhat trickier undefined case is incrementing a variable in the middle of an expression. In this example, it's undefined whether I is incremented before or after it's used as the index for the array A. A good compiler will flag all of these situations and many more. You should pay attention to those warnings so you don't have to chase these bugs down during system operation. There are a number of existing language use guidelines and tools that can help you improve your coding style. Perhaps the most famous is MISRA C, which was originally developed for safety-critical automotive applications. There's also a C++ version of this language guideline. MISRA C emphasizes the use of the C programming language in critical systems. This means that it intentionally makes the trade-off of eliminating some potentially useful language features to provide significantly reduced risk of defects. This means that it intentionally makes the trade-off of eliminating some potentially useful language features in exchange for reduced risk of defects. As an example, it forbids the use of recursion and dynamic memory management using calls such as malloc. While both of those techniques may be acceptable in non-critical desktop software, in embedded systems, these language features were deemed too dangerous to be acceptable. MISRA C emphasizes code portability and avoiding high-risk language features. It also sets forth best practices for safety-critical software. It can improve the reliability of any C code, but is best used for mission-critical software that can live with more restrictive language use in return for improved software reliability. As this figure shows, the 2012 version of MISRA C, with its security rule addendum, includes well over 100 rules, some of which are advisory, meaning they're nice to have, some of which are required, meaning that you need to do them but you can deviate if need be, and some of which are mandatory, which means you have to do them. Additionally, there are 17 directives that are generally not suitable for automated checking, but which are either advisory or required as well. CERT, which deals with security advisories, created a coding standard for C, C++, and Java to improve software security. An example rule would be that you are not allowed to use unbounded string operations because of the risk of buffer overflow. The CERT publications also include a list of tools and which coding rules they're able to check. In conforming to these guidelines, it's helpful to use tool support. Static analysis tools act more or less like compilers, but instead of generating code, they generate warnings. One type of especially useful warning is called a strong typing warning, which warns when variables which have the same underlying machine type have different meanings, such as feet versus meters. There are many static analysis tools, both commercial and free. If you want to get started, you can use GCC with a lot more warnings turned on than just WALL. You might think that -WALL generated the maximum possible warnings, but in fact, the set of warnings was frozen for compatibility reasons, and there are many, perhaps dozens of warnings past -WALL that you can turn on that can be very helpful. Dynamic analysis tools go beyond static warnings and instrument running programs to find problems at runtime. A classic example of dynamic analysis is looking for memory array bounds violations or resource exhaustion. A good starting point is the Valgrind toolset, which includes memory buffer checking. There are commercial tools as well as free tools for all of these functions, and the point of this discussion is not to recommend a particular tool, but rather to encourage you to look into tools that you will find useful for your particular situation and budget. This is an example rule from MISRA C. This is Rule 13.4, which states that the result of an assignment operator should not be used. The rationale for this rule is that assignment operators can impair the readability of the code and can introduce side effects. A couple examples are given, such as a sub x equals y, where the assignment statement x equals y is used as the index for an array, and the notorious if statement with a single equal if bool var equal false, where it does not compare them, but rather assigns false to boolvar and then uses the result as part of the if statement. Both of these uses are generally a bad idea and can lead to bugs. Worth noting is that the category is advisory and it's said to be decidable. What they mean by decidable is that a static analysis tool can tell whether this rule has been violated or not, making it possible to automate detection of rule violations. Beyond just passively finding errors, you can use good language style proactively so that the compiler can help you avoid mistakes. One example is you should always use an enum instead of integers for enumerated values, such as those used in switch statement cases. In this example, we've defined a color with specific color values that are permissible instead of trying to use #define integer values. More generally, use the const keyword instead of #define. Const can be very helpful because it imparts typing information. So in this example, if we use #define x to set a value to 1, that would result in a code bug because x would default in most compilers to a 32-bit integer, and shifting a 32-bit integer by 40 bits is generally undefined behavior. But because we defined x as a const, the compiler knows that this is supposed to be a 64-bit operation, avoiding a potential bug and avoiding the need for a cast to clutter up the code. Continuing the theme of trying to avoid #define, you should also use the inline keyword instead of #define so that you can avoid almost all macros. Inline gets rid of the subroutine call overhead for short subroutines of perhaps 10 lines or fewer. If the compiler complains the subroutine is too big to be inlined, then probably the overhead for the subroutine call ends up not mattering. Next, you can use typedef with static analysis strong type checking to avoid unit errors. In this example, we have different typedefs for feet and meters. While it sometimes takes additional hints to the static analysis tool so that it knows you want strong typing, a tool could detect in this case that we're attempting to assign feet to meters without doing the appropriate conversion. A bug like this involving a mismatch between English and metric units was responsible for the loss of the Mars Climate Orbiter mission in 1999, which burned up in the atmosphere of Mars rather than entering orbit. Finally, because embedded systems have varying word sizes, it can be extremely helpful to be explicit about the size of a variable, such as using int32_t for assigned 32-bit integer instead of plain old int. The standard int.h header provides a standardized C language way to do this. It's sometimes said that for every rule there's an exception, but exceptions should be rare and well considered. Deviations from language style guidelines should be done with extreme care. In some cases, you can do a blanket deviation when a rule simply does not apply at all to a code base. However, turning off entire rules because there are one or two exceptions is bad practice. In some cases, a rule will have to be violated for an excellent reason in one specific place or another. For example, in a code base that has both feet and meters, a feet to meter conversion will have to violate strong typing at the point of conversion. But the way to do this is not to turn off strong typing, but rather to have a one-line deviation for that one line of conversion code. That deviation should be accomplished by turning off the rule for that one line using, for example, a pragma, and should have a comment justifying exactly why that rule and only that rule is turned off for exactly that one line of code. It is common to have legacy code which generates lots of static analysis warnings because the code base was inherited in bad repair. And it may be impractical to fix everything all at once. So there are three general strategies to be used in this situation. Strategy 1 is to fix one module at a time to make the code compile clean for that one module with no warnings. This can be useful if you're doing refactoring or reengineering on a module-by-module basis. But note that you may need to keep warnings permanently off for third-party code modules if you only have headers and not source code. Another strategy is to turn on one warning at a time for the entire code base and then go fix all the places that warning is generated. For example, early on you might want to turn on the warning for uninitialized variables and fix all of them. When you get some time to do some more work, turn on the next rule, and so on. This will get you incrementally better code without having to rewrite the whole code base. Strategy 3 is to throw the bad code away and write it from scratch, potentially recovering high-level design information. In the long run, this tends to be the most cost-effective, especially if you have a bunch of old spaghetti code. However, it's hard to get the time and budget to do a complete clean slate rewrite. A useful compromise can be to find the handful of bug farms, rewrite those, and then use a more incremental approach for the rest of the code base. An entirely different approach to making your code less buggy is, instead of using a bug-prone language and finding the bugs, switch to just using a better language. There are some well-known desirable language capabilities. These include type safety and strong typing. In other words, having pointers and ints be the same data type is pretty much a bad idea, even though that's what C does. Maybe you want memory safety, where the bounds and arrays are actually checked automatically instead of you having to do it. Maybe you want some robust static analysis built right into the language rather than having to buy expensive fancy third-party tools. In general, a desirable language capability is there are no surprises. Well, it turns out such a language already exists and has been around for decades. It's called Ada, named after Lady Ada Lovelace, who was the first programmer. And here's an example program interface in Ada. This is the interface to a subroutine that increments a value. The value to increments is x, and it's a counter type, both input and output. The with clause tells you what the interface does. For example, there are no global variables, and the output x only depends on the input x. There's a precondition that x must be less than the maximum counter type, and there's a postcondition that the new x will be the old x plus 1. Note that this is not actually the code. This is the interface, which allows you to check things like proving that programs will never overflow a counter because you know what a counter does and you know what the interface looks like. The actual code to increment the value is actually pretty straightforward. You add 1. Ada's gotten a bad reputation because it was a very complicated Baroque language, but a subset called Spark Ada is getting traction as a safety-critical language. So it's a subset of the full Ada programming language that just keeps the good parts. It's a formally defined language, so you can verify programs mathematically. The language does not have ambiguities and does not have undefined behaviors, which obviates the need for a lot of the things that you saw in the MISRA C rules. You can actually prove that a program is correct. For example, you can prove before you ever run it that you will never overflow an array index, you will never divide by 0, and so on. Now in practice, when you write code, what you find out is you fail the proofs, but that's okay. This is static analysis on steroids that really gets you to get your code cleaned up before you can actually get past the compiler. A key idea is design by contract, where those preconditions and postconditions and side effects we were talking about are defined in advance, making it harder to have defects caused by mismatched expectations between different parts of the code. Good language style can make it easy for the machine to compile the code into the thing you actually wanted it to execute. And it can also be a very cost-effective way to find bugs automatically. You should start by adopting a safe coding style, considering either MISRA C or CERT C or a combination as your starting point. Your project coding style guides should specify one or more static analysis tools and the configuration settings, even if it's just GCC plus a dozen or two warnings passed minus WAL. This will let you automatically check language-specific coding style and avoid wasting time on that at peer reviews. Once you have static analysis set up, consider adding dynamic analysis for even better defect detection. As with human coding style, the point of good language use style is to avoid bugs. Let the compiler help you by finding the bugs automatically before the humans even look at the code. There are some pitfalls for coding style. The first pitfall is thinking that just because the code passes tests, all those warnings don't matter. You might be passing tests because your tests are very weak, because you got lucky, or because, in general, this particular version of the compiler just happens to behave the way you need it to. Next, beware of real bugs that are found by the static analysis tools, but you don't see them because they're lost in a sea of warnings of things you decided were false alarms. An important reason that your code should compile clean is that you might not notice a new warning pop up if it's buried in thousands of other warnings. So it's better to compile 100% clean to avoid this. Finally, make it a bit painful to deviate from style rules. This is because if it's easy to deviate, you'll find that everyone has an excuse to deviate rather than spend the slight extra effort to clean up the code. Every deviation should be formally documented and should result in the code still compiling clean.